So we are going to talk about the formation of a nucleus, right? So let us talk about nucleus. Now, all of us know that if we have a nucleus, let us say X, whose atomic number is Z and mass number is A, then the number of protons which are present is Z, that's Z, and number of neutrons which are present here, number of neutrons present here is A minus Z. Okay, this is number of protons and number of neutrons, right? So a nucleus basically consists of this, right? A nucleus consists of Z protons and A minus Z neutrons. All right. So, so when this nucleus is formed, what happens when this nucleus is formed? When this nucleus is formed, what happens? This Z protons combines with A minus Z neutrons. It combines with A minus Z neutrons to form what? To form nucleus. To form nucleus. Alright? Okay. So what I mean to say here is Z into mass of proton. This is what I mean to say. Plus A minus Z into mass of neutron. This is the meaning basically. This combines to form what? This combines to form the nucleus X with atomic number Z and mass number A. Okay, all right. And इसका जो mass है, I am saying this is mx. So when this is formed, energy is released. When this is formed, energy is released, and this energy is called as the binding energy. This energy is called as the binding energy. So when this nucleus is formed, from the free protons and free neutrons, I am talking about the free protons and neutrons. Okay, I'm talking about the free protons and neutrons. So when this nucleus is formed from the free protons and neutrons, then energy is released, and this energy is called as the binding energy of the nucleus X, of the nucleus X. So if you want to break this nucleus, again into its constituents, you'll have to give this energy. And if you want to form this nucleus, then this energy will be released. Okay. So what did we understand from this? We understood that if there is a formation, right? So if this, Z protons, Z protons, if this Z protons, they combine with, A minus Z neutrons. These are protons and these are the neutrons. Then they will form a nucleus with Z protons and A minus Z neutrons, right? So it will form a stable nucleus. But along with that, some energy will be released. So, what is happening? So energy is released during the formation. Energy is released during the formation of the nucleus. And that energy is called as the binding energy. All right. And when we talk about the breaking of the nucleus or the splitting of the nucleus, so in the splitting of the nucleus, into its constituents, constituents means what? Protons and neutrons. Into its constituents, energy is required. You have to supply energy. Energy is required, or we have to supply the energy. We have to supply the energy. This is also called as binding energy. Is the same amount of energy. It is the same amount of energy that is released during the formation of the nucleus, and it is the same amount of energy that is required that is required to break the nucleus into its constituents. All right. So this is a very important point that इस न्यूक्लियस के बनते वक्त जितना एनर्जी रिलीज होगा, इस न्यूक्लियस के टूटते वक्त भी उतना एनर्जी रिलीज होता है, तोड़ने के लिए भी उतने ही एनर्जी की जरूरत होती है। तो इसके बनते वक्त जो एनर्जी रिलीज होता है उसको भी बाइंडिंग एनर्जी बोलते हैं। मतलब द एनर्जी दैट इज रिलीज ड्यूरिंग द फॉर्मेशन ऑफ द न्यूक्लियस इज आल्सो कॉल्ड एज बाइंडिंग एनर्जी, or the energy which is required to break the nucleus into its constituent parts, constituent protons and neutrons, is also called as binding energy because the amount is same. All right. Okay. Now let us talk about the mass defect. Okay. So we will talk about the term that is mass defect of a nuclear reaction, which is very very important. Okay. So I'm going to talk about the mass defect of a nuclear reaction. So let us talk about this nuclear reaction which we had discussed now. तो अभी हम लोगों ने जो न्यूक्लियर रिएक्शन डिस्कस किया था वो क्या था? वो ये था कि जो, क्योंकि we are basically talking about the nucleus, इसलिए this is a nuclear reaction. This is not chemical reaction. Okay. So when I'm talking about Z times the mass of proton plus A minus Z times the mass of neutron is giving me the nucleus. Okay, that is m mass of x. Okay, the nucleus I'm getting, and plus I am getting what energy. Okay, so ये जो मैंने mx लिखा है, this is basically my nucleus here, whose mass number is a and atomic number is z. Okay, तो इस केस में यहाँ पे एक्सपेरिमेंटली ऑब्जर्वेशन एक किया गया है, राइट? इट इज ऑब्जर्व दैट, क्या ऑब्जर्व किया गया है हियर? इट इज ऑब्जर्व दैट कि ये जो न्यूक्लियस फॉर्म हो रहा है, ये जो न्यूक्लियस फॉर्म हो रहा है, इस न्यूक्लियस का मास, ये जो न्यूक्लियस फॉर्म हो रहा है, इस न्यूक्लियस का मास इस मास से कम पाया गया है। यानी प्रोटॉन और न्यूट्रॉन से, मान लो कि यहाँ पे 10 प्रोटॉन है, लेट मी टेल यू, 10 प्रोटॉन है और 12 न्यूट्रॉन है, तो यहाँ पे भी 10 प्रोटॉन और 12 न्यूट्रॉन ही है न्यूक्लियस बनने के बाद। ठीक है, पहले 10 प्रोटॉन और 12 न्यूट्रॉन अलग थे और न्यूक्लियस बनने के बाद वो साथ में आ गए, दे हैव कम टुगेदर। लेकिन जो मास है वो सेम नहीं है, जो फाइनल न्यूक्लियस है उसका मास थोड़ा कम पाया गया। इट इज ऑब्जर्व दैट द मास ऑफ द स्टेबल न्यूक्लियस, मास ऑफ दिस न्यूक्लियस एक्स, ठीक है, जो ये न्यूक्लियस बन रहा है एक्स, तो इसका जो मास है, मास ऑफ दिस न्यूक्लियस एक्स इज फाउंड टू बी लेस देन द इनिशियल मास ऑफ द सम ऑफ द प्रोटॉन्स एंड न्यूट्रॉन्स, उससे कम पाया गया। तो ये बड़ी आश्चर्य की बात है कि ये मास गया तो गया कहाँ, राइट? तो फिर मालूम पड़ता है कि ये जो मास है, दिस हैज एक्चुअली कन्वर्टेड इनटू एनर्जी। ये जो यहाँ पे एनर्जी मिल रहा है उसी एनर्जी में ये कन्वर्ट हो रहा है। मतलब ये जो मास डिफेक्ट आ रहा है, ये जो मास है यहाँ पे, जो मास डिफेक्ट हो रहा है, मास जो यहाँ पे थोड़ा लॉस हो जा रहा है मास का, वो जा कहाँ रहा है, वही मास एनर्जी में कन्वर्ट हो जा रहा है। दैट मास इज कन्वर्टिंग इनटू एनर्जी। तो यहाँ पे जो मास डिफेक्ट है, मास डिफेक्ट क्या है देखो, तो मास डिफेक्ट बहुत सिंपल टर्म है जिसको हम डेल्टा एम से रिप्रेजेंट करते हैं। तो डेल्टा एम क्या होगा? डेल्टा एम होगा ये जो फाइनल मास माइनस, मतलब जो ये जो इनिशियल मास है माइनस फाइनल मास। इनिशियल मास क्या है? इनिशियल मास है z इंटू मास ऑफ प्रोटॉन, z टाइम मास ऑफ प्रोटॉन प्लस a माइनस z टाइम्स मास ऑफ न्यूट्रॉन, ये है इनिशियल मास। इस इनिशियल मास में से ये जो मास है mx, ये घटा दो आप, दिस इज कॉल्ड एज मास डिफेक्ट। तो ये जो मास डिफेक्ट है, दिस इज कन्वर्टिंग, दिस इज ट्रांसफॉर्मिंग इनटू एनर्जी ड्यूरिंग रिएक्शन। ओके, so this is the point. So this mass defect, is transferred into energy. This is, try to understand this, this is transferred into energy during this during the nuclear reaction. Okay, it's very very important point. I'm sure all of you are able to understand. Okay, so now let us talk about what is the energy of this mass with energy. What is the relation of this mass with energy? We'll talk about that, which is called as the mass energy equivalence. So our next point is, mass energy equivalence. Okay, so we will talk about this mass energy equivalence. Okay, so आप लोगों ने atomic mass unit तो सुना हुआ ही है. You have heard about this atomic mass unit. I'll just recall this for you. AMU. ठीक है, atomic mass unit. So we should know one thing, that generally atomic and nuclear mass, atomic and nuclear masses, they are measured in what? They are measured in atomic mass unit. Okay, so we should remember this point. They are measured in atomic mass unit. This is called as AMU, or कभी कभी ऐसे बोलते हैं AMU छोटे में. Okay, ठीक है. So it is given as, so it is given as so it is given as 1 AMU is equal to 1.656 into 10 raised to minus 27 kg. Right, so this is the value of 1 AMU. This is very, very important. You might have, the mass of proton, right? It is almost equal to this, and this is also almost equal to the mass of neutron. Although there is a slight variation in that, but okay. So in a nuclear reaction, if delta M is the mass defect, then what would be the energy? Let's talk about that. So in nuclear reaction, if delta M is the mass defect, okay, if delta M is the mass defect, then the amount of energy that will be released will be how much? Then the amount of energy, then the amount of energy that is released, the amount of energy that is released will be how much? So that is given by Einstein's mass energy equivalence. That will be, okay, that energy will be E is equal to delta mc square. Okay, delta mc square. So if you put all these values and multiply, delta m ka value is 1.656 into 10 raised to minus 27, and c square, c is the speed of light, that is 3 into 10 raised to 8 a whole square. You will get this in joules. Okay, you will get this in joules, and you can convert this into electron volts if you divide it by 1.6 into 10 raised to minus 19. So it will convert into electron volt. Okay, so this value will come out to be 931.5 into 10 raised to 6 electron volt. That is 931.5 mega electron volt. So this is the value of 1 AMU, okay, in energy. So we have converted this mass, that is in kg, in terms of energy, that is electron volts. Okay, so it will help us to understand the future concepts. So this was the concept of mass energy equivalence. Now we'll discuss one more concept, that is called as binding energy per nucleon. So let us try to understand what is this concept of binding energy per nucleon, because this will help us to decide whether a nucleus is stable or not, or which nucleus is more stable. So binding energy per nucleon, this concept will help us to compare the stability of two nucleus, or two nuclei. So let us talk about this. So first of all, what is the use of this? Let us write it down. So it is used to compare the stability of different nuclei. So if you want to compare it, right, which nuclei is more stable, all right. So to compare the stability of different nuclei, we use the concept of binding energy per nucleon. Okay, we use the concept of binding energy per nucleon. Okay, now what is this binding energy per nucleon? It is represented by this BEN. So this is actually equal to total binding energy of an element divided by its mass number. So the total binding energy, that is the total energy released during its formation, total binding energy of an element X, Y, Z, any element, divided by what? Divided by the mass number of that element, divided by the mass number of that element. All right, mass number of that element. So it is basically the total binding energy divided by the mass number. Okay, so this is A is the mass number, Z is the atomic number. Okay, okay. Now if delta M is the mass defect, right? Now if what? If delta M is the mass defect, then अभी अभी आपने देखा था कि जो इसका बाइंडिंग एनर्जी है, जो इसका बाइंडिंग एनर्जी है वो क्या होगा? वो हो जाएगा डेल्टा एम सी स्क्वायर. तो बाइंडिंग एनर्जी पर न्यूक्लियन कितना आएगा? वो आ जाएगा डेल्टा एम सी स्क्वायर बाई ए. वो क्या आ जाएगा? डेल्टा एम सी स्क्वायर बाई ए. सो दिस इज द एनर्जी रिक्वायर, दिस इज द एनर्जी विच इज रिक्वायर्ड टू रिमूव वन न्यूक्लियन फ्रॉम द न्यूक्लियस, ऐसा बोल सकते हैं. So what is this? This is the energy which is required, to what? To remove one nucleon from the nucleus. So this is what is binding energy per nucleon. So I'll just tell you how it is used to compare the stability. So first you please note down this. So let us take an example to understand this better. Okay. So let us take this an example to understand this better. So we are going to discuss binding energy per nucleon as a stability criterion. Okay. So let us discuss this through an example. So what we will do is we'll consider here two nuclei. One is iron, another is bismuth. Okay. So if we consider two nuclei, so एक हम ले रहे हैं फेरस, फेरस मतलब आयरन, जिसका मास नंबर 56 है, दूसरा बिस्मथ जिसका मास नंबर है 209. ओके. और इनका जो बाइंडिंग एनर्जी है वो दिया गया है आपको. बाइंडिंग एनर्जी ऑफ दीज न्यूक्लियाई, टोटल बाइंडिंग एनर्जी जो है आर, वो आपको दिया गया है. तो बाइंडिंग एनर्जी जो है फेरस का वो आपको दिया गया है 492.8 मेगा इलेक्ट्रॉन वोल्ट, और बाइंडिंग एनर्जी जो आपको दिया गया है बिस्मथ का वो आपको दिया गया है 1640 मेगा इलेक्ट्रॉन वोल्ट. ठीक है. ओके. तो आप देख सकते हो टोटल बाइंडिंग एनर्जी किसका ज्यादा है? टोटल बाइंडिंग एनर्जी बिस्मथ का ज्यादा है. ठीक है, टोटल बाइंडिंग एनर्जी. लेकिन आप देखोगे स्टेबिलिटी आयरन का ज्यादा है, वो अभी हम प्रूव कर देंगे. तो टोटल बाइंडिंग एनर्जी जो है वो ज्यादा है बिस्मथ का. ठीक है. अब हम लोग देखते हैं कि बाइंडिंग एनर्जी पर न्यूक्लियन क्या है. ठीक है. लेट अस कंपेयर द बाइंडिंग एनर्जी पर न्यूक्लियन. ओके. तो बाइंडिंग एनर्जी पर न्यूक्लियन अगर आप देखोगे आयन का, ठीक है, पर न्यूक्लियन, तो वो होगा टोटल बाइंडिंग एनर्जी डिवाइड बाय उसका मास नंबर. ठीक है. उसका जो मास नंबर है वो कितना है? वो तो 56 है. वो हो जाएगा 492.8 556. इसको आप सॉल्व करोगे तो ये आएगा 8.8 मेगा इलेक्ट्रॉन वोल्ट. और अगर आपने फाइंड आउट किया बाइंडिंग एनर्जी इसका बिस्मथ का, अगर आप देखोगे बिस्मथ का, तो बिस्मथ के लिए पर न्यूक्लियन बाइंडिंग एनर्जी क्या होगा? बाइंडिंग एनर्जी ये 1 1 कर लो, ये 2 2 कर लो, 2/8. तो इसका बाइंडिंग एनर्जी कितना है? 1640. इसका मास नंबर कितना है? 209. तो ये आप कैलकुलेट करोगे तो ये आपका निकल कर आ जाएगा, ये निकल कर आ जाएगा आपका 7.84. ठीक है. तो दिस विल बी 7.84 मेगा इलेक्ट्रॉन वोल्ट. तो अब आप यहाँ पे देख सकते हो कि जो बाइंडिंग एनर्जी पर न्यूक्लियन जो है वो फेरस का ज्यादा है. राइट. बाइंडिंग एनर्जी पर न्यूक्लियन जो है फेरस का वो ज्यादा है एज कंपेयर टू बाइंडिंग एनर्जी per nucleon bismuth का. So this means what? This means that removal of one nucleon from ferrous is more difficult, as compared to removal of one nucleon from bismuth. So okay, this means what? So this means that this means that the removal this means that the removal of one nucleon from Fe is much more difficult, or requires more energy, right? This means that a removal of one nucleon from ferrous requires requires more energy as compared to whom? As compared to bismuth. This means Fe is more stable. This means Fe is more stable nucleus. Okay, I hope, I'm sure you have understood this point very well, that Fe is more stable. तो जिसका binding energy ज़्यादा है वो stable है, ऐसा कोई जरूरी नहीं है. जैसे बिस्मथ का binding energy ज़्यादा है as compared to ferrous, लेकिन बिस्मथ जो है वो ज़्यादा stable नहीं है, ferrous ज़्यादा stable है. क्यों? क्योंकि जो बाइंडिंग एनर्जी पर न्यूक्लियन की बात हो रही है, तो बाइंडिंग एनर्जी पर न्यूक्लियन वो फेरस का ज्यादा है, इसलिए फेरस ज्यादा स्टेबल है. दिस इज मोर स्टेबल. क्योंकि अगर आपको इसके एक न्यूक्लियन को बाहर निकालना है तो यू हैव टू गिव 8.8 मेगा इलेक्ट्रॉन वोल्ट, लेकिन अगर आपको बिस्मथ के एक न्यूक्लियन को बाहर निकालना है तो यू हैव टू गिव ओनली 7.84. तो विच इज मोर स्टेबल, बताओ?
Fe.
Fe. Very good, very good. So we'll discuss the last topic for today's lecture, that is the variation of binding energy with mass number. Okay, so we're going to discuss this graph, which is variation of binding energy per nucleon with the mass number. Okay, so this is just one simple graph, but a very important graph. Okay, so we'll discuss this and we'll end today's lecture. Okay, so let us take, this is the y-axis, this is the x-axis. Okay, so on these two axes, this axis we are going to take binding energy per nucleon. All right. Okay, okay. So this is binding energy per nucleon. All right, and here we are taking the mass number. Mass number means total number of nucleons, right? That is, all of you know, A, that is the number of protons plus neutrons. All right, so let us say this is 50, this is 100, this is 150, this is 200, this is 250. Okay, so we have taken this. So we find that now this is 0, let us say this is 2, and this is 2, this is 4, this is 6, this is 8, and this is 10. So what do we find? We find that this variation, right, it goes up like this to around let us say 7 point something here. This is for helium, then it again comes down, again it goes up a bit for carbon, then it comes again little down, then it is for oxygen, again it comes down, and then it goes like this, like this, like this, like this, like this, and then it comes down like this. So not too down, but maybe this till this point, or let us say this point. Okay, so this graph, so when we study this graph, we find that the binding energy per nucleon is maximum for ferrous. It is maximum for ferrous. Okay, this is found to be maximum for ferrous. Its value is somewhere around 8 point. We देखा था आप लोगों ने, somewhere around 8.7. So this is the graph. This shows that ferrous is the most stable, और इसके अराउंड स्टेबिलिटी डिक्रीज होती है, इसके इधर भी स्टेबिलिटी डिक्रीज होती है. ठीक है, इसलिए इधर वाले न्यूक्लियर फ्यूजन करके इधर आना चाहते हैं, इधर वाले न्यूक्लियर फिजन करके यहाँ आना चाहते हैं. तो वी विल स्टडी अबाउट फ्यूजन एंड फिजन इन द फ्यूचर लेक्चर्स. ओके, ठीक है, टिल देन बाय. सो आई एक्सप्लेन यू दिस मोर. राइट, ये सबसे स्टेबल है, फेरस इज द मोस्ट स्टेबल. तो इधर वाले जो लोअर है, दे विल डू फ्यूजन and they want to come here and they will undergo fission, nuclear fusion and fission reactions, right, to become more stable. So they all want to come in this middle region to become more stable. Okay, ठीक है, so ठीक है.